Yeah. All right. Okay, so go ahead and get started. I should have the stoplight code from you, the digital representation activity, and your drawings. Those are all due today. So is everybody good with that? Okie doke. So we're going to do some talking first about 3D printing because that's what a lot of you are going to use for your projects, and that's what the next assignment is going to be related to. And then we're going to do some CAD work interactively. And I don't really know how long it's going to take us to get through that, so we'll see how fast we go. But I want to make sure that everybody knows how to use it because you're going to need to for your projects. And did everybody bring a mouse of some form? Looks like, okay, yeah. What?
For the project,
Uh-huh.
for example, we want to have some components that will be printed use the 3D printer,
Uh-huh.
and we haven't have those components from the like some um, syringe, so we need to measure the size, and then we know what's the kind of frame we are going to build using the 3D printing.
Right.
And in that case, we buy those components, or you buy those for us.
So we can probably buy them for you.
Okay.
So definitely still, if you have ideas of what you need for your project, go ahead and start sending us the parts that you need so we can start putting together the order.
Okay.
Yeah. So sensors, all that kind of stuff.
Okay.
And there will be in, let's see, Thursday's lecture, towards the end, I've got a couple slides that are just tons of places that you should go online and look for materials. And then hopefully over the weekend you can go ahead and get together the parts list for your project. Anything else? Okay. So we're going to go over how to use Onshape in the very basic way and some 3D printing stuff. Onshape is actually pretty complicated. It is very similar to SolidWorks, which is the design program that a lot of industrial engineers use. But it is in the cloud, so it has a lot of the same features, which can get pretty hairy. They've got really great resources on their website. If you go, you can watch some videos of how to do things. They have weekly webcasts. They have a bunch of tutorials. It's worth looking at. And they have a Getting Started series. I think it's 7 videos or something like that for this Getting Started series. Each of them is probably 5 to 10 minutes. And it's really worth going through if you're going to use this to design parts for your project. I went through them a few months ago, and when I started using Onshape, I switched from SolidWorks, and it was really pretty easy. And the 3D printing that we're going to talk about, you can do it a lot of places. I think everybody here is going to be using the campus service. So through the library, you can go library makespace and submit your 3D print file, and then you just go to the service desk and pick it up when they email you and say it's done. That's really nice because you don't have to deal with the maintenance and the care and the feeding of these machines, which is a lot. And you'll go through your print and you'll get halfway through or more than halfway through, and maybe the extruder will jam, or maybe there's a power glitch, or there's 1,000 things that can happen that can make the prints go bad. But luckily, you won't have to worry about any of that using their service. But if you're ever somewhere not here and you're looking to do 3D prints, hacker spaces or maker spaces are all over. And there's actually one here in State College downtown. They're spreading like crazy. Most of them have 3D printers, laser cutters, mills, lathes, tools that are too expensive or too bulky for most people to have in, especially like New York City, where everybody's paying a fortune to live in a broom closet. Libraries, like our library, are starting to get into 3D printing as a service, including some of the public libraries. And then there's online services like Shapeways that we've talked about. Those are called service bureaus, where you can send your print into them, they'll make it on their huge, expensive printers and then ship you your part in a week or so. So these are some examples of prints gone wrong. I was telling you that things can go wrong very quickly. For example, here something happened partway through and it just, I guess they stopped it. This is a problem with a shift where somehow the printer coordinate system got shifted. This was supposed to be Walt Disney, and it's clearly not. You can start dragging the print head and mushrooming out the top of the print because something didn't secure well. Here, whatever this animal was, its head is now strung out because of an overhang problem in the design that was unsupported. And a lot of these parts, something like this, life-size head, would probably take 20, 30 hours to print. So the printer had probably already been running for 12 hours when this problem happened. And so that's really unfortunate when you're that far into a large print and something goes wrong. So I said you probably don't want to maintain one of these because it is a lot of pain. And they can also do things like spontaneously catch on fire. So you have to watch out for that. Understanding the tool chain of how a 3D printer works is going to be pretty important, so you know how to go from the CAD file that you design to the 3D print. Some of these steps will be taken care of for you if you use the library. I'll tell you what those are, but it's helpful to know what's going to happen to your design because that can help you figure out where things could go wrong, and they will. Also, if you design it in millimeters and that's not specified when you send the file off and they interpret it as in inches, things can get bad pretty quickly. But it all starts with a CAD tool. So this is the SolidWorks logo. It could be anything. I'll show you several CAD tools. But you do your part design in some kind of tool and generate a 3D model of the part. You then save that model as a stereolithography file, or .stl. And there's a lot of backronyms for what STL means. The most common one is standardized tessellation language, but you can see it takes the part and it breaks it up into this mesh, and that mesh is what's saved, and you can do that at different resolutions. Then you take this STL file and you take it to a program that's called a slicer. This is the equivalent of a CAM piece of software for the machines that we saw when we went over to Ellis's shop. What the slicer does is it goes through and actually generates how the machine is going to make the part, what tool paths are going to be used. And it saves that out as a file called a G-code file, which Ellis talked about some as well. It's called G-code files because you can see there's G and then a code and then some positioning commands here. And then that G-code file is fed to the 3D printer, and that's what actually creates the print. So when you send your file, I would say you'll probably be best off sending the library an STL file because they may not know how to read whatever, if you send them a Parasolid file or something from your CAD tool, they may not know how to read that. But if you go with an STL file and send that off to a service bureau, they'll take care of the slicing and G-code generation because that is machine specific. Each different machine, you're going to do the G-code a little bit of a different way. It's kind of like when they run the CNC lathes at the shop, they have a post-processor that they run the G-code through for each different machine. Does that make sense? All right. So each step in a little bit more detail. The CAD, originally we used CAD just to make 2D flat drawings like what you did with what you turned in. And CAD tools have advanced to where you can make 3D drawings with them. And in fact, now a lot of times I make the 3D model of the part and don't ever make a 2D drawing if I'm going to send this off to a service bureau to have it made because I don't need a 2D drawing. They're going to take the 3D model, plug it into their tool chain and go. So you can use a variety of these. That was Onshape, which we'll look at. This is one that's called OpenSCAD, or OpenSCAD, depends on who you hear say it. It is free and open source, so you can go download it, install it on your machine. It's a much different way to interact with a CAD tool. You write code to create the part. It's got its own little sort of programming language. In fact, I'm going to go ahead and show you what that looks like. So we'll open it up here. It's really nice because you can create variables for, say, a part width or spacing between holes or hole sizes, and then you can change them and the part will change. So let me render this design here. As you can see, I have M3 clear, M3 tap, so metric 3 clear and tap hole sizes, some clearances, how thick I want the wall to be, how wide, all of these different parameters that I could change. And when it eventually generates here, which takes a little bit on a MacBook Air, we'll have a 3D model that we can send to the printer. And I've used this for a lot of designs. So here we go. So here's my model that was completely generated. And now let's say I want to change, I want these holes to be much smaller. So we can do it again. Again, it's going to re-render. But this gives you a lot of power because you can create parametric parts. Like say you had a part that held tubes in a centrifuge. Well, maybe 3D printing might not be the best way to make that if it's going to be really high speed. But you could have a parameter that says number of tubes, and you could enter how many tubes you wanted, and it would completely redesign the part to hold that many number of tubes for you based on the functions and the rules that you've put in there. So that's one really nice thing about these parametric tools. Yeah, so now you can see that those holes all change size because I changed that variable. And there's some other tools that are like this as well. You can drive things like SolidWorks and Onshape with equations, which we probably won't actually look at today, but there's a video on their website of how to do it if you're interested in using equation-driven bits. And then generating the STL file. So say your CAD model, these two red dashed rings, so we have like a cross-section of a tube here. The STL file will not perfectly reproduce that because it is tessellating, right? It's meshing. So you can see here, well, it's a bunch of flat sides that are approximating a circle. So you have to export at an adequately high resolution with STL, otherwise your part will be very angular and not at all what you expected. And then you have to slice the file. This is where some of the magic, I would say, is in 3D printing. If you want to have a thing like this, it had to be built up in layers by the printer. And so the solid model was this shape, but now we have to slice it apart into layers that are the height that the printer is going to print, which in this case I think was maybe 0.3 millimeters or something. It wasn't very thick. So it does that, and it also generates any internal structure. Now, printing this entire thing as solid plastic would be really wasteful, and it would take a long time because it would have to travel and squirt plastic everywhere in here. So what we do is inside the part, we actually generate like a mesh network in there. You can do it in different ways. This is just a rectilinear grid, and that's one of the quickest to print. But it can also be honeycomb. It can be whatever shape you want. And you define some wall thicknesses. So for example, if you look through, you can see the support material for these pockets in the top. But this saves a lot of time on your print. It saves a lot of plastic. It makes the part pretty strong, really. And that's all done by the slicer. So you don't model all of this in your CAD tool. The slicer takes care of that for you and takes care of generating any support that's needed. But there's a lot of parameters. Like you can change how much infill there is. It's probably really hard to see, but this part has a really dense infill. The network is really, really close compared to this. I did that because this part needed to be sort of strong, and this didn't. This was just to see if it would fit where I thought it needed to.
How long will it take to print this solid part?
So it's not quite solid, but it's almost solid. So this would probably take a couple hours. And this would probably take a couple hours as well, but it's a lot bigger. And the plastic isn't that expensive, but it's best to not use, wear on your machine and all that.
How thick does it need to be before you have to specify that you're going to switch to a honeycomb structure? Because I'm assuming if you have a thin, semi-thin wall, it's going to be solid, but...
Yeah, so there's a wall thickness parameter that you can adjust in your slicer. So you can see here, I think I have my wall thickness set at like 2 millimeters. So anything that was over 2 millimeters, it started shelling it out. Yeah. And there's lots and lots of things that you can change in there. I'll open up. This one is called Slicer. Different printer companies have different ones they recommend. Some of them even have their own. But in here, so there's print settings, so I can change the percentage of infill, the pattern, how many, after so many layers do I want it to do a solid fill. You can add what's called a skirt and a brim onto the part, and you can add a raft. So sometimes when you're printing these parts, I don't have an example that still has the raft on it, but you can see this one's actually a little bit warped on the bottom. As I was printing it, it started cooling and the edges peeled up, which is not good. So you can actually print a thin layer that is much bigger than this, that adheres to the print bed better, called a raft, and then print this on top of the raft. And then you just rip the raft off and throw it away later. So they might do that for you if they think your part needs it. A brim would be just adding some material around the edge that you'll peel off and nothing under it. So there's a lot of tricks. And for example, to get parts to adhere better to the bed, a lot of times we will use a combination of acetone and dissolved plastic and rub it on the bed. And the acetone will evaporate and leave this kind of tacky surface on the bed that this sticks to better. So there's a lot of tricks that are used in 3D printing. And then the slicer puts out the G-code. This is some G-code for, I think it was a DC-DT bracket or something like that. But you can see I generated it a couple years ago. And these are all comments. And then it's just all of these instructions. Move to X, Y, and extruder coordinates. Move to X, Y, and extruder coordinates. Here it's moving to a certain Z coordinate or a certain height. And these files, they're just plain text. And they can be, you know, like 20, 25, 50 megs for a relatively large part because it's telling the printer everywhere it needs to go. Some design considerations and some things to think about. Just because you can design it in the CAD tool doesn't mean it can be made in the shop, and it certainly doesn't mean it can be made on a 3D printer. 3D printers have this nasty habit of not liking to print over thin air. It's called bridging. So in this part, they just had, you can see, had a narrow end and a wide end, and they tried to bridge across thin air to see how it would go with this particular printer. You can see here on the narrow end where you're bridging maybe half an inch, it's fine. As you start bridging multiple inches, you start getting layers that don't adhere and start sagging. So you'd have to support that somehow, either with a permanent or a temporary support material. It just doesn't work if you try to bridge more than maybe a couple of inches at the most. And I think that's even kind of pushing it. I try to not do that. Overhangs are another problem. And I actually have a part in the office that has this issue of if you try to go very far at an angle that's greater than 45 degrees from vertical, again, you start running into the printing in thin air and it just doesn't work. So you need to support that again somehow. You can have your tool generate support material for you, or you can manually go in and, for example, on this part, if it wasn't critical that this space was open, I would just add, you know, a tapered gusset there at, I don't know, 30 degrees from vertical or something, and then you'd be fine. So does that make sense to everybody? See why you don't want to do it? If you are, so the angle I'm talking about when you're designing your part that you need to watch out for is any overhang that is greater than 45 degrees from there, you should support. It won't make it. You can print little test pieces. I'm sure they have these for the MakerBots at the library. This is what it would look like though, because this is printed on a MakerBot, that have different bridging distances and different overhang angles. So you can see these all look really good, and by the time you get out here, it's pretty ratty and pretty bad. But you should ask to see that kind of thing or look it up because somebody online has done it for about every printer. This is an example of taking a perfect sphere and then tessellating it at a couple of different resolutions so you can see what the effects would be. This one you could visibly see when you printed it that it was flattened surfaces and tessellated. This one you probably wouldn't be able to tell. And some of your parts, if they are a little bit rough, there is going to be some texture, just from the nature of having it 3D printed. You can put these in a box, spray some filling primer like you would put on a car on them, kind of shake it around the box, spray the primer. Do that a couple times, put a coat of paint on it, and nobody will know it's not a cast plastic piece. The other thing is the accuracy of the machine is not, I'm going to say it's not necessarily constant due to the machine and due to the thermal contraction of the plastic. So if you put in this CAD design, you might get something that's a little bit wider and the hole is a little bit smaller than you wanted. And unfortunately, this varies. The printer has different resolutions in X, Y, and in the Z. So the horizontal axes have the same resolution. The Z axis has a finer resolution. So if you have a vertical hole through a part versus a horizontal hole, it will have a different dimensional warp to it. So a lot of times people will print parts that have holes of, I want this to be 1, 2, 3, 4, 5, 6, 7, 8 millimeters horizontally and vertically, and then create their own little linear regression for if I want a hole that's this size, I need to put in a hole that's this size into my model because we just don't have that fine-tuned. So it's something to keep in mind. The other option is if you need it to be really, really tight tolerance, you can always ream it out with a drill bit later. Just make sure you have a thick enough wall thickness that you don't break into the filling material. A lot of times, though, the clearance isn't that critical on these parts. You can make it a little bit loosey-goosey and it'll be fine. You can also, if your end goal is to design something and you're 3D printing, a prototype like this, or let's say we were designing a wrench and we wanted to eventually have this machined, we could design features into this that there's no way the machine shop or the foundry is going to be able to make, because we can do stuff like put passageways that have strange shapes and turn inside the part. There are even some people that have printed parts and then halfway through the print, they'll have a hole where we're going to put a nut or some other internal feature. They'll stop the print, put in the hardware, and start the print again and actually encase the part inside the print. So you can't really do that in the shop. And this is a part that was 3D printed at MIT. It actually has fluid passageways all throughout here, and this is a fluid reservoir. This was all printed at once, basically. And when they press that, this becomes a hydraulically actuated finger, and they're using it on robots. So it's really cool. We couldn't make it in the shop, but if their end goal was to make this in the shop, they would be very sadly disappointed when they went and talked to the machinist. So think about what your end goal is going to be. You can put text on parts. We have a part in the lab that actually says rock mechanics on it that I 3D printed a long time ago for a lab. It has raised lettering, which is what we call embossed lettering, and this is engraved lettering. Generally, if your letters are going to be not huge like those are, you want to go with engraved lettering. Embossed lettering that's really small will probably result in the printer dragging filament all over the top of your part, maybe a failed print, and it also is something that can get caught on and sheared off pretty easily because such thin lines aren't very strong. So go with engraved lettering on your part if you need lettering. It is a nice way if you're designing a nice front panel for something to kind of dress it up a little. It's kind of a dark picture, but you can see there are some gears and some pins in this assembly that was all 3D printed. And a lot of the gears and things on 3D printers are themselves 3D printed, so you can make working mechanical parts pretty easily. But you need to consider the clearance, just like you would when you're designing something to go to the shop. So how much clearance do you need between these parts? On 3D printed parts, true dimension clearance, if you need something that's tight, something that's going to be a press fit, maybe 5 to 10 thousandths of clearance, I would stay on the upper end of that, is a pretty good number. If you have something that needs to move and have a free fit, like those gears, or you need a pin to be able to slide through something, somewhere around the order of 15 to 20 thousandths is a pretty good clearance number. Wall thicknesses are a big one. They're bigger for injection molded parts than they are for 3D printed parts. But you can see by doing this, we're trying to maintain a roughly constant wall thickness. 1 millimeter is a pretty good wall thickness to shoot for in a lot of your designs. If it's thicker, you may actually be wasting material, wasting time, and possibly end up creating a weaker part. If it's a lot thinner, the part will just fall apart. I've got an example here, and I'll send these around. But you can see I tried really thin wall thicknesses up here, and you can actually see through the part in places. So you don't want to go quite that thin. And those had quite a few failed prints. A big one to consider is that the strength of this part is not isotropic. It is printed in layers, and it is the weakest in the plane of whatever the z direction is. So for example, if we printed this little person figure and we printed it standing up like it is, the z layers would be like this, and it would be pretty easy to shear the person like this, but not vertically. So it might be harder to break their arm off, but it could be pretty easy to grab their head and just push it off to the side. So you could print it, you could turn it completely on its side, add some support material under here, and print it that way. Then it would be much stronger in the horizontal plane, but weaker in the vertical plane. This part is a little bracket for the lab, and actually I ended up printing it sitting like this on the printer because this was the plane that I cared about least. I wanted to have more strength in this direction. And this big hole produces overhangs that are over 45 degrees when you get towards the top of it. And so by printing it like this, I got around that problem completely. Another way you can do that is make the hole a little bit bigger and then put something flat across the top where you only have 45s there, and then it's just a bridge, a small bridge across the top of the part. So I'll send that around too, but you can see how that works. And you can see as it was printed, sitting with this end up, there's a little bit of droop in these holes, but not much. And that's something that you should specify when you send your print. If it needs to be printed in one orientation, they have an undergrad working at the library that is going to take his best guess at what you meant for your part to be. But if there's something specific, you should tell them. There are a bunch of places that you can go online to get 3D models. McMaster Car, where we buy a lot of hardware, has 3D models for, I'm not going to say almost all, but for a lot of their things. If you wanted to download the 3D model for the nut that you guys drew for the activity last class, you can go do that and just pull it right into the CAD. There's another website called GrabCAD. They have tons of random stuff, parts, regulators, gauges, all kinds of stuff that you might need a CAD model for. Thingiverse, that's worth showing you. This was a website started by MakerBot originally, which is now owned by Stratasys. But you can go on here, and these are people that have shared their designs for all kinds of stuff. So we can, let's say we want to look at things. So these are the newest. So here's a bracket for a stepper motor that somebody designed and put up there. So you could just go grab this file, do any modifications that you needed, and use it. So don't reinvent the wheel if you don't have to. And there are also some government agencies. NASA is one that you can go download almost any of their space probes, the space shuttle, all that kind of stuff. You can go download a file for it and 3D print it if you want one. It's kind of neat. They also have 3D prints of some comets. I think it was through the USGS, somebody had some downloadable, like you could get maps of faults and that kind of thing that you could 3D print. People 3D print topography all the time. In fact, if you go on Thingiverse, somebody has the State College area topography as a 3D print file. And that one, actually, you would think that you would print it, like, let's say this is going to be our print of State College. You would think that you would print it on the printer bed like this, and you would build up the topography. But remember I said the Z resolution of the printer is a lot higher. So the best way to print that part to have the highest resolution is to print it like this, where the topography is sticking up this way, and get a much better quality print that way. And yeah, if you Google, there's tons of stuff out there. Some of the commercial software, so we talked about SolidWorks, which I've used and liked it. AutoCAD, I've used and liked that. Photoshop, I never have really got into designing parts in Photoshop. It seems like the wrong tool for this job. And Rhino. Rhino is pretty expensive, but if you have a Mac, they're in beta for Mac right now, and you can get it for free. So that's kind of nice. They're a curve-based modeling tool, and I played with them some and didn't settle on using them for everything, but it might be worth checking out and see if you like it. There's a bunch of free stuff. OpenSCAD that I've already mentioned. You can use Google SketchUp to design parts and assemblies if you already know how to use SketchUp. Sculptress is more of an artsy one. You don't put in dimensions, but it's kind of like molding clay with your mouse. So if you're doing something that's a little more artistic, that's a fun one to check out. And you can also design something in a CAD tool and then bring it into Sculptress and touch it up. FreeCAD has the goal of being an open source SolidWorks. It's still relatively early in development and unfortunately still relatively buggy. I have used it and had some parts printed and machined from it, but it can be kind of frustrating at times. Blender is a pro tool and used for animation, that kind of things a lot. I never have used it for 3D printing. Autodesk 123D and Autodesk Inventor you can get through the university. They're not bad at all. And Tinkercad, which is completely online. And Tinkercad is really simple, which means you can't design horribly complex parts in it, at least not easily. But it gives you things like you drag a cube onto the part, and okay, now there's a cube, and then you can size it. And then you can drag letters on or drag other shapes on and just kind of play around with them. It's an easy way to get into designing things. But I think you'll probably outgrow it quickly if you try it. So, excuse me. The assignment, which is due on the 13th of October, because I do not know how backed up the printers are at the library right now. So don't put it off, because you don't want to submit your job and get the email that, like, oh, we'll have your print ready in 7 days, and it's the 12th. If there is an unreasonable backup, if people are getting told that, you know, we're 4 weeks behind, then we'll adjust if we need to. But what you should do is design a part and have it made. It could be something for your project. It could be something not for your project. May not be that far along in your project yet. But these are all examples of stuff that you could do. This is part of a pulley that is here. And I don't know if this is glued together or not. Yeah, this one's glued together. So you print 2 of these. You see it's got these pegs and holes, and they lock together, and you get this nice pulley. That's another trick if you have something that's going to have overhangs, no matter how you print it. It's just to cut it in half and make some way to join it. Some little brackets. This thing, I think I actually have, yeah. That's a sensor case. You can see there's places for air to flow and some screws to mount it to something. This is a laptop stand. It has the Apple logo cut into it. Some little brackets for the lab. This holds a geophone and an Arduino. Whatever you want. You can go download something, but you can't just print whatever you download and turn that in. You have to do some modification. So for example, I downloaded this Arduino stand, and then I added this block on the side that has these posts and that place for the geophone and all that. So either create a part from scratch or go modify something and turn it in. Everybody good? Okay. Another thing that you can consider for your projects, this is a part that I feel pretty lucky about how well it printed, actually. You can see it's got some complex geometry in here to hold, in this case, a ring of LEDs. But I needed some things to be held on here in a more secure way than I thought you could do by just threading the plastic. You know, if you thread the plastic, it works for a few times, and then the threads wear out. You can get these little brass inserts from McMaster Carr. If you make the hole in the plastic the right size, you hold this brass insert on there and you melt it in with a soldering iron. And so now I have brass threads melted into the plastic, and those threads won't wear out. So it's a good way to secure stuff together in a stronger way. And these are pretty cheap, and you can get them in everything from, I think, number 4 screws, which is what these are, all the way up to like 3/8 inch bolts. But I don't have a soldering iron big enough to melt those in. So if you do that, good luck. But anything small like this, it's pretty easy. So keep in mind that those exist. And now we're going to design some stuff in Onshape. If you want to look at some of this stuff, there's a bunch of parts up here, like things that hold servos, that actually goes into there. It's what it was designed to do. The wrench, some brackets, some little plates. Even something like this can be useful if you need to space something in the lab. Say you need to raise something up a precise distance. You can just print plates for it. It's a pretty cheap way to do it. So go ahead and fire up Onshape. And I am going to try to sit back here with a keyboard and mouse and do this with you all, and we'll see how it works. All right. So is everybody in Onshape? Okay. So we're going to do a couple of parts, depending on how much time they take. See if we can make this a little bigger. Maybe. All right. So this is one part that we're going to do. This holds a DC-DT. In fact, I can show you what it looks like. So this is in our lab. This is a magnetic base that holds the DC-DT, and we're going to design this bracket right here, which there are 2 of in this setup. So in this case, we're going to have 1 tapped hole right here, 2 through holes for those riser posts, and then a through hole for the DC-DT. And then if we have time, we will design something like this that has, we've got all these teeth on here, and it would be a real pain to draw. So we're going to talk about patterning and use that. So once you're in Onshape, go ahead and click Create. And I would make your document public because it doesn't matter. We're not designing anything proprietary here. So I'm going to call it Class Demo. And then you should get to this screen. So give everybody a second to get there. The view cube? Yeah. So there are a few parts to their interface, and this is pretty common to most CAD tools. You've got some kind of tool strip up here, which we'll go over some what it does. And then what Robert was pointing out was this view cube, which is pretty common. If you can click on any of these faces and instantly get to that view. Like if I want to view the top, or this corner view, or front view, or however you want to view your part. If you hold your right mouse button down and drag, you rotate. If you hold the left mouse button down and drag, you select. And you'll notice that if I drag to the right, it's blue. And if I drag to the left, it's orange. And this is determining whether you have to have just the edge of a part in to have it selected, or if you have to have the entire thing included. I'll show you how that works in a second. And then you've got these planes. Oh, and to pan, you hold the middle mouse button. So hold your scroll wheel, and you can drag around like this. It's also nice if you have a plane selected, or if you're working in a sketch, you can hit N, and it gives you a normal view. So you can, if you get lost, you hit the question mark, and it brings up all these keyboard shortcuts which if you use this much, you'll get used to them very quickly because they save you a ton of time. But I'm going to try not to use them since you can't see what I'm pressing on the keyboard. If I do, yell at me. All right. The whole idea of making parts in this kind of a CAD environment is by sketches, and then we extrude or we make a pocket from the sketch, or we pattern something on the sketch. And a sketch is just a 2D entity. So for our thing, we need, click the top plane, so that the top plane is highlighted like this, and then come up here and click Sketch. All right. Go ahead and click the little pencil by this, and I'm going to call it bracket base so that my sketch has a name that's descriptive. Otherwise, when you have 20 sketches, you will be very sad that you did not name them. And then up here is all the different geometries that we can draw. So I'm going to go ahead and press N. So I'm looking straight down on my sketch. And I need a rectangle for that part. So here's a rectangle. And if you click this little down arrow, you see that there are two types. There's a corner rectangle where you define the two corners opposite each other. And there's a center point rectangle. Well, it's most useful for me to do the center point rectangle because I want this entire part to be centered on the origin of my coordinate system here. So go ahead and click center point rectangle. And notice when this little dot's the origin. When I hover over it, it gets yellow and it's selected, which means that I am going to constrain the center of my rectangle to be on the origin. So go ahead and highlight it and click. And you see now I can drag out a part. Don't worry about getting the dimensions of this exactly, or really even close when you're doing this. You'll drive yourself crazy. So just drag out a shape and click. And I'm going to hit escape. And now you see I have my mouse pointer back. I can grab these faces and vertices and change this right now. That means it is unconstrained. Blue lines mean that there is something unconstrained about this sketch, which is what you don't want in your part design. We want to have everything nice and tied up. But let's go ahead and create the rest of the geometry, and then we'll do some constraining. For circles, if you click the drop-down arrow, you see you can do a center point circle, a 3-point, or an ellipse. We want center point circle. And we've got 3 of these, right, on this sketch plane. So go ahead and hover over the origin until it highlights again and drag one out. That's going to be the hole for our DCDT. And then you'll notice when I get up here to this x-axis line that you see these little orange dashes come out. That means that it's going to constrain my circle to lie on that x-axis, which is really handy. We don't have to do that ourselves. So click and drag and go over here and click and drag. So is everybody here? You missed a step. Okay, what'd you miss?
Your top bar changed.
Yes. Oh, so double click bracket base there.
Yeah.
And now you're in the
Oh.
sketch editing it. So go ahead and hit N to get in a sane view there. And
Is
then
there any way you can space those circles, or just estimating for now?
right now they're just wherever we dropped them, which we'll fix in a second. In fact, to delete pieces. Yeah. So you can either, so I'm going to hit escape so I get my pointer back. You can either click on it and hit delete, or this should be a good chance to show you this, how this drag thing works. So if I left click and drag to the left where I get the orange box, you see I just get that line. Now if I right click, you see I get nothing, because whatever I'm selecting has to be completely enclosed. So for example, now if I do this and I let go, I select the circle but nothing else, which is kind of handy if you do the right drag. And if I did a left drag, it would select everything that that box touched. Okay, give people a second to get to get to the same place. And just for fun, I'm going to go ahead and put one of my circles not on that x-axis line so we can see how to fix it if that happens. And this is way easier than it was even a few years ago. So it's awesome.
Is there a way to just take one piece and then, like control C, control V it?
No.
Okay. So if I wanted another piece of identical diameter size, I need to draw that out to the same size again.
We'll constrain it in a second, yeah. So we'll use constraints to do all the sizing. All right, so let's say here, I'm going to hit escape so I get my pointer back. Here I screwed up. This circle can be anywhere. That's not what I want. I want it to be constrained to here. I can just hold it over there, or in this case, that's actually going to be the easiest. Just hold it over there like that, and then let go. And now it should be constrained to lie along that axis. All right, so now we have a sketch. Go ahead for now and click the green check mark, which means I'm done working in this sketch, even though it looks pretty wonky and not like the part we want. And so you see it's just a 2D feature. We need a 3D part. So in this left side here, click the sketch, so bracket base. And up here, there's this extrude, or Shift E. Click that. And now we see that our part has popped into 3D. You can grab the arrow and change it. Or what I always do is just enter in here. So for now, let's say that we're going to make it 0.25 inches thick, like that. And then I'm going to name this bracket boss, since this is the boss of the piece that's coming out, like that. So now we have a 3D part. And in theory, we could send this to the 3D printer or to the machine shop, but we would be very sad because it looks not right at all. So has everybody got a 3D part? Yes? No? Okay. Don't be afraid to stop us, because this is tricky the first time you see it, and the second and the third, and about the 300th it becomes less tricky.
How do you change the name of the extrude? It doesn't let me do it.
When you hover over right here by the green check mark, a little pin comes up, and you click the little pin. And for reference, the green check mark means I'm done, save, and the red X means don't save anything I just did. This is all version controlled as well, which I'll show you at the end. But all right, so now we've got this. Here's the nice thing about these kind of tools. Go back here to this bracket boss sketch, or sorry, the bracket base sketch, double click, and we'll hit in. So now we're back to our 2D sketch, and we have some work to do. So first, click the two circles here, so that they're both orange. And now we're going to...
You have the lines, like the lines over right there.
The what?
Line. Like you have the all your lines
Oh,
going
hit P. Yeah, so P turns on and off the planes. So here you can see the planes. If I hit P, they go away. And if I hit P, they come back. I generally leave them on, but it's a preference. So now we're going to apply a constraint to these. This is the constraints menu. So click the little down arrow. And I want these two circles to be equal sizes. So you click equal. And now they will change together.
It's just size 1 to one of the others.
Right, but
How
now,
does-
but if
I
you,
guess it doesn't matter, but does it constrain to the bigger one or the smaller one?
I don't know which way it goes. it doesn't really matter because now they're both the same size, yeah. And now we need to tell this what dimension we want those to be. So this is your dimensioning tool. This little, the two ticks with the arrow. So go ahead and click that. And click on one of these, your favorite one, left or right circle. It's like left or right Twix. And yeah. And when you do, you'll get this diameter call out that's coming up. And we're going to click. And now you would enter the size that you want it to be. So for now, let's say 1/4 of an inch, 0.25, and enter. Now, we have 1/4 of an inch piece of rod coming through in reality. Physics.mtu.edu, tap and clearance drill sizes. And you get this chart. We want 1/4 20, which is right here. And we want a free fit, which should be 7/64, right? Or 17/64. Here's the cool thing. We can go back here and you just type 17/64 and it does all the math for you. You can also, let's say we want to do this as a 5 millimeter hole. So you just type 5 mm, enter, and it does it.
So what I type mine is,
Do what?
go ahead.
Oh, it's sizing the entire thing,
Yeah, that's what I was gonna say too.
not the whole. Or at least it changes,
Keep
so
it in perspective, right?
Yeah.
it's the perspective, but.
So we'll fix it as we're going along here. So 17/64, so 0.266. Everybody good there? All right. We're still in the dimensioning tool. If you're not, click to get back in it. Click on this center one. And let's say that we're going to make this, we'll give 20 thousandths clearance to our DCDT. And I know the DCDT is, let's see, it's 3/4 of an inch in diameter. So it's 0.75. So we want to add 20 thousandths clearance, so 0.77. We already see we have an issue, right? Where this is bigger than what I drug out. It's probably smaller than what you did, or somewhere in between, right? It's different. I'm going to hit escape so I can drag this a little bit bigger. All right. Go back into my dimensioning tool. Now we could dimension, like you can click this line and say exactly how long you want that to be. We could click here and specify that. But design intent, I want this to scale. If I change that hole in the center, I don't want to have to go back and update all of these dimensions. That would be awesome. So I can click the line and click the circle, and now I can specify the distance there. And so let's say that I want 1/8 of an inch, so 0.125. And now there's going to be 0.125 inches on either side of the circle, the outside edge of the part. And you see that some of the lines have turned black. Like this circle is black, these lines are black. That means they're fully constrained. So we can't drag them around anymore. We're done as far as they're concerned. Let's do the same thing here. I'm going to say, let's say 1/4 of an inch here. And we can say 1/4 of an inch here. Those are somewhat redundant. We could get around that if we wanted to, but for now, we'll call that good enough. And notice we still have some unconstrained parts. So if you hit escape, yeah? So we can click and drag, and you can see that I don't have the width of this constrained. So we could specify some distance from here to here, or we could specify the entire length of the thing. You could do it a bunch of different ways. For now, let's say that from the center of this circle to the center of the part is going to be 1 1/4 inches. All right. So now everything is fully constrained. The entire sketch is black, so we're good to go. And you click the check mark. Everybody have that? Yeah? Okay. So now we have something that looks a little bit more like our part. There. Now we need to have this hole that goes into the part, into that center bit. So we're going to make another sketch, but this time we're going to make the sketch onto a face of the part. So if you click and select this front face so that it's orange, and click sketch, and we'll rename this, I'm going to call it 256 hole, because that's what it's going to be for a 256 screw. So now we're sketching, if you hit in, we're sketching on this face. And we want to put a center point circle. And you can kind of mouse over the origin and then go up so that we're constrained to be on that vertical line, and drag a circle on there. So now I've got this circle that is constrained to be in the center of the part and of some unknown size. Does everybody have that?
John, I'll ask you on the last this. How'd you get this?
How did I get what?
How did you get from the last place that we were at to here?
Ah, okay, yeah. So let me delete this and I will show you again. So you're here, right? All right. So you select the face that we want to do the sketch on. So like we would click on this front face so that it's orange.
Okay.
And then click sketch. And name it. Okay. So does everybody have a sketch on that face now? All right. So then we're going to grab this center point circle tool. Come in here. We go where we've got this constraining line above the origin there and drag it out. And then we go back for a 256. We want to make this a tapped hole. So tap drill is a number 50, which is 70 thou. So I will get my dimensioning tool. You can hit D or you can grab it 0.07.
Can you only do that if you have a completely constrained?
Can you only make the new sketch?
Well,
Or,
so mine is not constrained. If something went wrong, I didn't have time to fix it. But,
okay, let's see
so
what you
this
got.
is
You have conflicting constraints.
yes, but so I wasn't able to then add that
Okay.
to it when I was.
I'm going to borrow your mouse for a sec, and I will remove. I think this guy's the.
Okay.
Yeah. So now it should let you. If you click the green check, it should. And I would just delete that one
And make it again.
and make it again. To right click on it. Yeah, if you need to delete a sketch or anything, you just go over here and I'm still in it. That's fine. You go over here and right click and you can delete. Like that. Good? Okay. Now, we need this circle to be centered on the part. And there's several ways that you could do it. I'm going to show you how to do it with construction lines because we haven't gone over how to do those yet. So we're going to select the line tool up here. And then this one that's solid and dashed like this, you select it. That's the construction line tool, which means these are lines that we're going to use to build the design, but they're not going to be made. They don't mean anything in terms of when we send this part off. And so I'm going to click down here on the origin. I'm going to go up and click on the center of the circle. And then I'm going to go from the top center of the part down to the center of the circle. Double click. So now I have two lines. I have this line and this line. Are people there? Yeah? No? Okay, what's going on? Okay, so, oh, you didn't tell it a sketch plane. So double click, click the face.
Oh,
Yeah.
so you have to
Now you
define
can
it.
add the circle. Yeah. Okay, and now I'm going to hit escape, so I have my pointer back. If you select these two lines, so I'll click that line, so they're both highlighted. And then in our constraints menu, we say equal. It will force both of those lines to be equal length, which centers our circle on the part, no matter what the size of the part is. You just click one and then click the other, left click. Oh, so you're still drawing lines. That's what the deal is.
Oh, what else was I supposed to click?
Okay, yeah, let's undo that. Because you have lots of lines. Okay, so now draw another line from the center to the top, or top to the center, however you want to do it. And now, so double click where you ended to end drawing the line. Yeah, there you go. And now hit escape so you have your pointer back, and then you can select both. Oh, scroll wheel. Scroll wheel. Hit the equal constraint. Yep. Does everybody have this centered hole? What's up? Oh, so where you clicked it, you've actually constrained it to be on the origin, which is why it won't move. So here's what happened. I'll show you on here. So if you click if we do a circle, see you had the origin highlighted when you did this, and so it's constrained to live on the origin. So just delete it and draw one out here.
Honestly, once you just figure out what all the buttons actually are, the rest of this is actually fairly intuitive. So
Yeah.
that's kind of nice.
So give people a couple minutes to catch up.
Assume we're all found.
Okay. So go ahead and click the green check mark because we are done with that sketch. And we're going to select the sketch over here on the left-hand side. And then again, click the extrude. And if we zoom out, you can see what it's trying to do, which is it's trying to make this a pin coming out. And that is not at all what we want. We want to remove material. So you're going to click remove up here. Instead of add, want to remove. And now it's going an inch into the part, which is putting it all the way through here and end over here. That's not what we want either. We could specify a depth, but remember that would kind of go against design intent. If we change the part to be much bigger, maybe it wouldn't be a through hole then. So in this menu that says in type, say up to next, which means it's going to go up to the next face. So now, if you look, it's gone through there, but nowhere else.
So it goes through the next phase as well.
Right, yeah.
Okay.
And then you click the green check mark. And now you have a beautiful, almost finished part here. What we need to do is, remember I had nice rounded corners on that one in the picture. Why not? It's a 3D print. We can make it as nice as we want. So up here, now that we're in the 3D view, go to the fillet tool, which is just to the right. This is loft, and then thicken, and then fillet. And click fillet. And now every edge that we click on, it's going to do a fillet operation on. So we want to click on these vertical edges only on the edge of the part. So I click it, and boom, I get a nice, in this case, a 0.2 inch radius fillet, which is fine. So now we just go around and click on all 4 vertical edges. Like that. Until we have this little filleted part. Did people have fillet working? No. What? So you would select these vertical lines here. What's that? You can make stuff really fast in here. Is it working? Yeah. Okay, and we'll go ahead and click the green check mark. Now let's say that we wanted to do some chamfering on these. It's not necessary for this part, but just to show you how to do it. So click chamfer, which is next to fillet. And let's chamfer where these rods are going to go through. Now when you first click, it's a 0.2 inch chamfer, which is a little extreme for this. So let's chamfer it to 20 thousandths. If you do that and then just click somewhere up in here, that looks a lot better. So I'm going to go ahead and chamfer both sides of those holes. Like that. So that is not a bad looking part. That's basically what we wanted to accomplish. Does everybody have this or some semblance of very close to this? All right, so this would be the tool that I would recommend you use for doing your 3D printing assignment, to design something in here. I'm going to show you, I don't think we have time since we've only got 3 minutes for everybody to follow along with this one, but I want to show you patterning and mirroring because it's, I think, one of the more important things. So I'm going to click the plus button down here and create a new part studio, which means I'm creating a new drawing basically. And I am going to go ahead and make a sketch here. Like I said, don't worry about trying to follow along unless you just are dying to. I'm going to dimension this thing. I'm going to say that that is 5 millimeters. I'm going to say that that is 150.
You started a new.
I started a new one, yeah. Actually, I'm going to make this, let's go with 10.
So how to save footprint this one?
It's always saved.
Okay, so
Yeah.
we don't need to worry about saving.
Yeah, there is no save button. Okay, so I'm going to do this, then I'm going to extrude it. So I click, extrude. I'm going to extrude it 100 millimeters. All right, so now I have this vertical plate standing here. But I'm going to cut a bunch of teeth into it. So I'm going to select one edge, make a new sketch. I'm going to zoom in up here, and I'm going to draw with lines a triangle. I'm going to click the corner, click here, and click back there. So now I have a nice little triangle. I'm going to go ahead and dimension that. That here, I want it to be 1 millimeter. From there to there, I want it to be 0.8 millimeters. Now, I want this to be an equilateral triangle. So I'm going to select the 3 sides, say equal. And now we have conflicting constraints because I did something that was not smart, probably. So if you have conflicting constraints, they highlight in red, you can select them and hit delete and try to figure out what went wrong. The other way we could do this is by putting an angle dimension in. So between these 2 lines, I want it to be 60 degrees. But we still have a constraint conflict somewhere. And these are some of the trickier problems to figure out, unfortunately. All right, so if I delete that dimension, okay, so it can't be equilateral, right? Because I had it 0.8 deep. So now we're fully constrained. I'm going to click check. I'm going to select that sketch. I'm going to extrude, remove, and I'm going to say through all. So now if I look, I have 1 tooth cut into the block. So only 150 more to go. And you don't want to do that manually. That would be horrible. If you have to do something more than a couple times, there's probably a better way to do it in CAD. So I'm going to take that extrude, and up here is a pattern. I want to make a linear pattern. I want them to be 1 millimeter apart. I want there to be 150 instances. And I'm going to pattern, we need to pattern a feature. I'm going to pattern extrude. In the direction, you can just select this line here. I want to pattern in that direction. I want to pattern in this direction. And it's working. And something very interesting happened. Let's undo it and try that again. Sometimes you just hit the X. All right, pattern. We want a feature pattern. We want extrude. And direction, we want that line. And we want to do it at 1 millimeter. And let's just say we want to do 5 of them so we can see if we're going to work or not. There we go. If we flip the direction, now we have 5 of them. It was trying to put them off this end. Now we're going to say we want 150. It's going to think for a second. We're going to have 150 teeth. Awesome. Now, the reason I only designed this with teeth on one side, though I want it to look let's say like this with teeth on both sides, is because I can leverage everything I just did, excuse me, by selecting, it's hard to see from way back here, somewhere up here there is a mirror command. There it is. I'm going to select mirror. I want to mirror a part. I can just click it. And the mirror plane, I want to mirror it across this plane. And I hit check. And now that is the part that I actually wanted. I only had to design half of it. And you just mirror it. Using mirroring and patterning will save you hours when you're designing complicated parts. So everybody kind of sort of feel like they could drive this and only get mildly frustrated. All right. Well, if you have questions, find me. Otherwise, I'll see you Thursday.